So in this lecture, we're going to talk about probability. There are three main concepts that I want you to take away from this discussion. The three main concepts are how to compute probabilities of disjoint events, how to compute probabilities of events in the case of a discrete uniform probability, and conditional probabilities together with Bayes' rule or Bayes' theorem. So those are the three things that we're going to cover. One of them is going to be trivial. Okay, the disjoint events is going to be trivial. In fact, the entirety of it is written right here. Computing probabilities in the case of discrete uniform outcomes. Well, now that we're experts in counting things, we should be able to compute probabilities of discrete uniform outcomes. And Bayes' rule and conditional probabilities, we're just going to cross our fingers and hope that goes well. So, I will also say that I'm going to ignore a lot of formality here, and a lot of the things that I'm going to say here are either formally speaking incorrect or incomplete. But what I'm going to say here is, in my opinion, the best presentation for almost anybody who's not going to be a mathematician studying probability theory. Right? So there's a lot of formality that I'm skipping here. If you end up in grad school and you're taking a theory of statistics course, then some of the formal things I'm sweeping under the rug here might matter. Okay? But for almost any situation that you're going to find yourselves in, as long as you don't go to grad school in probability or math, or in statistics or math, is good enough. Okay? So if you're interested in kind of what formal things am I sweeping under the rug, send me an email or schedule some WebEx office hours and we can talk about it. But I imagine for all of us, this is going to be good enough. Okay, so we're going to talk about experiments. So experiment could be dealing 5 cards from a 52-card deck, or it could be choosing 3 people from a group of 10 people. Experiment could be flipping a coin 3 times. So we have lots of different experiments, and we have outcomes. So we know what the word outcome means. It's just a result of the experiment. So flip a coin 3 times, heads, tails will be a possible outcome. Right? So the sample space is the set of all possible outcomes. So mathematicians, I think, tend to prefer omega for the sample space, and non-mathematicians seem to prefer S. So for us, S is going to be how we're going to denote the sample space is the set of all possible outcomes. An event is a set of outcomes. Okay? So if S is the set of, and for us, an event will be any set of outcomes. And here, this is where I'm sweeping a lot of formality under the rug that'll never ever matter unless you end up in some theory course. So for us, an event is any set of outcomes. But if you go take a theory course, then it's not just any subset, it's one of a specified set of special subsets, and we're going to ignore all of that. Okay? So just think about an event as any set of outcomes. If S is the set of all possible outcomes, then an event is just a subset of S. Okay? So the events are just the subsets of S in this case. Right? So we talk about probabilities of events. Okay? So I have a set of outcomes, I perform my experiment, and then I define or compute some probability of that event. Okay? What we mean is, so here I have a fancy P. P means probability of. So this means the probability of the event A, whatever that happens to be. So when I say probability of an event, I mean when I do my experiment, what's the probability that the outcome that actually happens, what's the probability that the outcome I observe is one of the ones in the set A. Okay? So for example, flipping a coin 3 times. Right? I could have heads, tails, and tails, heads. There are 8 possible outcomes that we know from our counting section. There are 8 possible outcomes. So my sample space would have 8 things in it. And just for example, one possible event. So there are lots of events. One possible event would be this. Right? So just heads, tails. The set consisting of those 2 outcomes. Right? So when I talk about the probability of A, it means I flip my coin 3 times. What's the probability of getting one of these 2 outcomes? Okay? And there, it's 2 out of 8. Right? There are 2 outcomes here, 8 outcomes total. So probability of getting one of these 2 is 2 out of 8. So here's an example. So I have an event is a set of outcomes. And the probability of that event is what's the probability that I actually observe one of those outcomes in the event. Okay? So there's a little bit of formal versus informal use here, is I don't talk about the probability of individual outcomes. Okay? So outcomes are elements of the sample space. events are subsets of the sample space, and formally speaking, I only ever talk about the probability of an event and not the probability of an outcome. So for example, you could say, what's the probability of observing heads, heads, tails? And, well, I could write one of these two things, right? This one is incorrect. This one is the one that's correct. It's because I don't talk about the probability of an outcome. Okay? I don't talk about the probability of a member of the sample space. I talk about the probability of a subset of the sample space, right? So here, this singleton consisting of the single HHT outcome, the singleton consisting of that outcome is a set. Okay? And I can talk about the probability of that event. And this is the probability of observing heads, heads, tails. Okay? So there's a formal versus informal. But for us, that distinction will not matter. Okay? But formally speaking, we only ever talk about the probability of an event, which is a set of outcomes. Okay? So a lot of our events, well, a lot of times they're just going to be represented by A and B. We have set operations. If A and B are events, if they're subsets of the sample space, then A union B and A intersect B are also events. Right? So if we describe events by in words instead of with set names, how do the intersection and union relate to the description in words? Well, intersection corresponds to and union corresponds to or in the following sense. So if I say A is the set of all outcomes where I observe heads on the first flip, right? And B is the set of all outcomes where I observe tails on the last flip, then A intersection B is the set of all outcomes which are in both of these sets, which means if you just kind of think about it or write it down, A intersect B is the set of all outcomes where I observe heads on the first flip and tails on the last flip. Okay, so if I'm dealing with events using set notation, then intersection corresponds to and. When I'm dealing with events in just kind of the description in words presentation. Right? Similarly, if I had A union B, it would be the set of all outcomes where I observe heads on the first flip or tails on the last flip. So just like usual, just with our kind of intersection and symbol, union and or symbol, it means the same thing here. Okay? It's not a coincidence, right? That's kind of exactly how we used it before. So if I want to go back and forth between describing events using set notation and describing events in words, intersection corresponds to and union corresponds to or. So we should be comfortable with those kind of translations from set notation to describing events in words and vice versa. Okay. So first major concept here is disjoint events, right? So I'm going to think about my events and event diagrams. So I have S as the set of all possible events, and A is some subset of that, and B is some subset of that. And if I want to compute the probability of the union for disjoint events, right? So I've underlined and put a box around disjoint because it's important here. If I want to compute the probability of a union of two disjoint events, it's just the sum of the individual probabilities. Right? So what's the probability that I observe one of the outcomes in here or here? Well, since there's no overlap, it's just the probability that I observe one of the outcomes in here plus the probability that I observe one of the outcomes in here. Okay. So if we think about probabilities in terms of counting outcomes, which we will mostly be doing that, but not always. If I think about the probabilities in terms of counting outcomes, then I want to count the number of outcomes in here and count the number in here and just add them together because there's no overlap. I'm not double counting anything. So we have already covered the first major topic, which is probabilities of disjoint events. It's just the sum of the individual probabilities. Now we want to move on to the uniform discrete case, which is mostly about counting. Okay. Suppose I have some overall experiment which has some number of possible outcomes. This is what I want. So I have some sample space consisting of these possible outcomes, and I'm going to assume they're all equally likely. So what that means is the probability of observing this event, which consists of just the one outcome Si, is the same as the probability of observing this one outcome Sj for any different I and j. All these singleton events have the same probability, which we can call P. Okay? Then the total probability is 1. That's the probability of the sample space, which is the sum of the individual probabilities of the disjoint events, which is p times n, because each one of these individual singleton events has probability p, and there are n of them. So that's p times n, and so p is 1 over n. And probably we could have said that if these things are equally likely, then the probability of each one is 1 over n without any kind of computation in between. Okay? This is the discrete uniform case. Okay? So here I'm using probability for disjoint events is just the sum. Probability for a union of disjoint events is the sum of the individual probabilities of the events. Okay? So discrete uniform case means there are finitely many events and they're all equally likely. Okay? So the probability of observing any one of the individual outcomes is 1 over the total number of possible outcomes. Right? So when the flipping a coin 3 times, there are 8 possible outcomes. They're all equally likely. So for any individual event or any individual outcome, the probability of observing it is 1 out of 8. So heads, heads, tails is 1 outcome. There's a 1 out of 8 chance of observing it. Okay? So if I take any subset in this discrete uniform case, if I take any event, right, it's some subset of the sample space. So suppose it has m things in it. Well, the probability of A is the sum of the probabilities of the events consisting of single elements. And there are m of those, and they all have probability 1 over n. So the total probability is just the number of outcomes in the event divided by the total number of outcomes. Right? So in the discrete uniform case, if I want to know what's the probability of observing an outcome in the set A, I just count the number of events in A and divide it by the total number of possible outcomes. Right? So easy example. So I flip the coin 3 times. This is the same example I've been mentioning the whole time. So flip the coin 3 times. What's the probability of observing exactly 2 heads? Okay. So I've already written out the entire sample space. So the sample space is the space consisting of these 8 outcomes. Okay. So we know how to count. So I have 3 flips. Each flip has 2 possible outcomes. Their order matters with replacement. So 8 possible outcomes for the 3 flips. Okay. And I want to know what's the probability of observing exactly 2 heads. So I want to look at the event consisting of outcomes where I have exactly 2 heads. Right? I've already made these things into columns. Okay, so here's 3 heads, 2 heads for these 3. Each of these 3 events has the possibility of 2 heads. And these are 1 head and then 0. Right? So the event in question is the event consisting of these 3 outcomes, because those are the 3 outcomes in which I observe exactly 2 heads. Okay? Heads, heads, tails is one of those outcomes. Heads, tails, heads as another one, and tails, heads, heads. Okay. So the event of interest is the event consisting of these 3 possible outcomes, and there are 3 things there. So the probability of getting exactly 2 heads is 3 out of 8. Okay. So we know how to count, right? So I didn't have to write out the entire sample space. I say, how many total outcomes are there? It's 2 to the 3rd. Okay. What's the probability of getting exactly 2 heads? Well, I have outcome of the first flip, outcome of the second flip, outcome of the third flip. The only way for me to get exactly 2 heads is for me to take 3 of those places and choose 2 of them to put heads in. Right? So I get 3, choose 2. Okay. That's why there are 3 things here. So I have 3 outcomes, and I want to know how many ways are there for me to get exactly 2 of these 3 outcomes to be heads. Well, that's 3, choose 2, because I can choose 2 of those 3 spots to put the heads in and put tails in the 3rd. So here's another situation, slightly trickier situation. We're going to have to count in stages. So what's the probability of observing a full house? Okay. So remember, a full house is 2 of one rank and 3 of a different rank. So here rank means ace through king. So those are the 13 different ranks. And remember, I have 4 suits. So I have hearts and diamonds and spades and clubs. Right. So 52 cards. 4 suits and 13 ranks. So how many ways are there for me to get a full house?